Welcome to the video Bayesian estimation for measuring persuasion in small groups. What I hope to do in this video is to show you how to implement the model that we recommend in our paper called When Deliberation Produces Persuasion Rather than Polarization, Measuring and Modeling Small Group Dynamics in a Field Experiment by what's commonly referred to as the Fung collaboration group. And what I want to do is to give you a tutorial on how to use some software that's called OpenBugs in order to replicate the results in the paper. But also you'll see in the tutorial that the code that we distribute with this tutorial is very general and it's adaptable to many situations. So you should be able to apply the model as well to your own work if you're working with the kind of small group data that we're describing in the paper. What I don't intend to accomplish is first to explain why why we're doing this, what's the motivation or the theory for either the model or the application. So I'm assuming that you've read the paper and that you understand it and you're ready to learn how to do what we recommend in the paper. And the second thing I don't plan to accomplish is to show you how to make use of OpenBugs specifically. So this is not a tutorial video on OpenBugs. I have distributed a companion video alongside this one that is an introductory tutorial on the use of OpenBugs software. So if you've never used OpenBugs before, I strongly recommend that you stop this video now and watch the other video to at least learn how the OpenBugs platform works. Because you'll need to know that as I'm showing you how to implement the model. I'm assuming that you know how to use OpenBugs. And also, I'm not going to try to teach the theory of Bayesian inference more generally in this video. If you're completely new to Bayesian inference, you would do well to try to read a book or take a class on that. Although I think watching these two videos side by side might help you get some insight. If you've never seen Bayesian inference before, it might give you enough of an intuition of what's going on and maybe to motivate you to learn more about it. Okay, and so what I want to do is to show that the method that we recommend and the model that we show in the paper is a general method for modeling dependence in small group research, and then we use it in our paper to model persuasion. But you could use the model for other situations depending on what you're interested in your small group research. And so this tutorial is going to distribute some code that you can use to pre-process your data, all right, so that you can read out the data and essentially read it out into, to kind of format it the right way, and then read it out into, export it into OpenBugs so that OpenBugs can use it. And also you'll see the tutorial show you that that we presented a set of different kinds of models that are very flexible. So we have different versions of the model that it can accommodate continuous outcomes, dichotomous outcomes, or ordered outcomes. And then the code is also general for each of those models for the number of questions that you're going to include in your pre-post survey, the kind of outcomes that you're trying to model. For example, the topics that people are being persuaded on. And it's also general for the number of respondents. And the code is also general if you're doing modeling ordered categories. There's also a parameter you can give it to tell it how many categories you have. So in other words, you don't have to kind of rewrite the code to accommodate all these different situations. Those are all just parameters that are fed into the model. And so the models are flexible to these different kinds of situations. And I think that makes it easy for you if you want to adapt the code to your own research. Okay, to think about the motivation of why we want to have a model of dependence, why we want to apply a model of dependence to small group research. If you think about it, just intuitively, whenever people are talking to each other in a small group or interacting in some way, that you're going to end up seeing dependence and preferences among people within the same small group. So one way you might get that dependence is through a process of persuasion, right? So if somebody in the group makes a very strong argument about why we need to reduce taxes on the wealthy, the others might not have thought of that argument, and they might say, well, that makes some sense to me. And so their preference might move to some extent in that direction. And so as people are talking to each other and trying to persuade each other, that process of persuasion might be one way that you can create dependence. And then what we want to do is, for whatever the cause of the dependence, we want to, just in an econometric sense, to be able to accommodate it and account for it so that we get the right answers when we estimate the structural parameters. And so that kind of dependence is going to be almost always observed when people are interacting with each other, when they're talking to each other or interacting in some way. And indeed, that kind of dependence is exactly what we try to induce by design when we do small group research. So we really need to have some kind of general model that can accommodate that dependence. So as a general matter, typically, you could think of that there's two, big sources of dependence in small group research. One is from what might be called homophily, which is the kind of universal phenomenon that people like to talk to other people who are just like them. And so if people who are similar to each other self-select into their groups, then you'll see this kind of dependence, but just through that kind of self-selection process, and not necessarily due to anything that happens within the interaction. And the other way that you can get dependence is if the group interaction itself is causal. So for example, if that interaction leads to persuasion or some other effective process that the interaction induces some dependence on preferences. And so the model that we present in the paper accommodates for and models both types of spatial dependence. So if you have either or both of these types of dependence, you really need to use a model like the one we propose to accommodate the fact that there is dependence in small group research. But then, as we explain in the paper, what we're interested in is that second kind of dependence, the causal effect of interactions. And in order to identify the causal effect of interactions, then you need to have a design that's like a randomized control trial. And then in order to say that the effect of the interactions is causal, then you have to buy into and accept the assumptions that underlie a randomized control trial design. And the biggest one, of course, is randomization, but there's other ones as well. And you can read the paper if you want to learn more about what those are. But let's say you've read the paper and maybe you want to replicate our model, and you've agreed that the RCT assumptions are met in our application. Maybe you've collected your own data and you believe the RCT assumptions are met for your application. So if that's true, then we can really think about kind of modeling the interpersonal interactions as a causal effect. And then when you do, there's there still remains kind of two big categories of reasons for dependence that we might be interested in. So one of those kind of causes of group dependence is the group composition itself, which is to think that being exposed to a group of who themselves have some set of characteristics, such as maybe for example, if a liberal person was seated at a table with a bunch of conservative people, they might move towards the conservative opinion just through the group composition effect. Or if a male was seated at a table of mostly women, you could imagine that there's changes just due to exposure to the group itself, based on the observable characteristics of the other people in the group, or at least measurable characteristics. And then the second type of dependence is this residual form of dependence that remains even after you account for whatever those observable characteristics are, or measurable characteristics. So even once you've accounted for the effects of the group composition, there still might remain some residual dependence that you have to keep track of. And so the model that we propose models both of these types of dependence at the same time. But then it turns out, in order to model both types of dependence, for both types, we really have to we need to be able to set up our data and feed the data into the model in a way where we can keep track of who is nested within whom. And once you do that, then actually writing the model is not too hard. But before I go on too much further, I've got to acknowledge that the model itself is based on, it's just a slight complication of a model that Peter Congdon proposed in chapter 8 of his book, Applied Bayesian Modeling. So both the setup for the data that I'm going to describe next, and then the model that I'll describe just after that, largely derived from Congdon's book. It's just a slight complication of what he proposes. So if you're going to write up your results, even if you're going to use this tutorial and our code in order to generate your results, I really want you to cite Congdon's book, because really all of this is due to his what we've learned from his book. Okay, so the key challenge is to set up the data in a way that when we feed the data to the model is able to keep track of who's sitting with whom, and then get all the pieces of the puzzle in together in the right way. And so the way that Congdon proposes we do that is through these two variables, map, which is a variable that's going to keep track of the neighbors for each person, where a neighbor is somebody else who's in that same person's discussion group. And then a variable C that's going to keep track of the indexes in the map that belong to each person. So the example that I have on the screen here is a hypothetical example where we say that there's 4 people in each discussion group. And what I've shown here is a snippet of, this imaginary data for these 4-person discussion groups and what it would look like for the first discussion group. So here I is just the respondent that we're interested in modeling their preferences. So here we have, if we've kind of label everybody sequentially, for the first group, persons 1, 2, 3, and 4 are all in the same group. So that means person 1 is neighbors with persons 2, 3, and 4, right? So the map variable is keeping sort of listing 2, 3, and 4 as persons 1's neighbors. Then obviously person 2 is sitting at the same table with persons 1, 3, and 4, right? So map keeps track of that. And then I've left out person 3 just for space, and then person 4 is sitting alongside persons 1, 2, and 3. And so the map variable is just keeping track of who's neighbor, who is person I's neighbors. Obviously, if we went on to the next group, you'd have the next line of the code would be person 5, and if person 5 is sitting with persons 6, 7, and 8, then the next 3 lines would be, for the fifth, the next line for I would be 5. The next values for map would be 6, 7, and 8. So it just continues that way until you cycle through all of the groups in your data set. And then C is just keeping track of the index of the map variable that belongs to each person. So you can see C has to start, just for reasons that you'll see when we get to the code, it has to start at 0. So you start with the 0th index before you start the counting process. But then you can see C is saying that the 3rd index is the last person that belongs, that's a neighbor of person 1. The 6th index is the last person who belongs to person who's a neighbor with person 2, and so on. The 12th index is the last person who's a neighbor of person 4. And so you can see the map variable is going to end up being the length of the total number of neighbors that are in your data set. And the variable C will be the length of the number of people in your data set plus 1. Where that plus 1 is just because you have to add that 0 to start the vector. Okay, and so what you'll see when we get to the pre-processing tools is I have some R code that just generates these 2 variables that pre-processes these and generates these variables for you automatically. Okay, just to think about the application and to motivate the rest of the tutorial, I'm going to switch to sort of thinking substantively about the paper and sort of what those two types of causal dependence look like for our application. So the first, the group composition effect. We're interested in the effect of being exposed to a group of some composition of ideal points. So this would be, for example, if a liberal person was seated at a table of all conservative people versus a liberal person being seated at a table of all liberal people, and vice versa for conservative people. And so what's the effect of, a person with a given ideal point being exposed to a group of people who have a distribution of ideal points? And what we're modeling here is the propensity of their ideal point itself, this kind of underlying sort of measure of their ideology. How much does that change as effect of exposure to the discussion? And we're able to model those ideal points or identify those ideal points because we're nesting respondents within a set of questions. So you could think of that sort of like in an IRT kind of logic, that if we ask repeated questions that measure somebody's ideology, we're able to extract their ideal point as a latent variable. And so what we're doing for the group composition effect is trying to model how much that variable changes from the pretest to the post-test. And then for residual dependence, we are just modeling how much dependence is left for each of the questions that we administer in the survey after we've accounted for the person's changes in their ideal point. So once you net out the role of ideology, what does dependence, is there still some dependence left over for each of the different topics? And we call that topic-specific persuasion. So essentially what we end up doing is modeling these two, what you could think of as random effects or latent variables. One is delta theta, which is modeling the latent persuasion, and the other is delta zeta, which we call topic-specific persuasion. And so what I'll do for this tutorial is just use some simulated data. And the reason I'm using simulated data is just simpler than the kind of sort of messy, complex data that you get from a specific application. And also it's nice because the simulation data gives us some benchmarks we can see that we're hitting. And what I'm going to do is illustrate this with an example from the simulated data just for the continuous case, which is the easiest to consider. But then it's a straightforward application to a dichotomous case, or to what we have in the paper, which is an ordered case. Okay, so the model that we want to estimate is given in line 1 here. And so for each of the outcomes, the superscript is the time. So the post-treatment outcome is O1, the pre-treatment outcome is O0. And so what we have in line 1 is the systematic component of the outcome. And for each of the outcomes, we'll have a constant beta naught. And for reasons you can read in the paper, we have a structural parameter beta 1 for the pretreatment outcome. And if you could think of that, we include the pretreatment outcome because then what we're modeling is the difference in the change in preferences from pre to post test. For econometric reasons, we have to include the person's own ideal point, pretreatment ideal point in the model, and then scale it by the coefficient beta 2. And as I mentioned, I'm not going to show it in this video. You'll see it in the code, but I'm not going to dwell too much on it. But we are able to extract ideal points in the model, making use of an IRT kind of setup. It's for ordered data in our application, but it's just the same logic as an IRT. So we essentially just extract ideal points the way you normally would. Site is that with some abusive notation here, that's going to be the list of exogenous variables. In our case, the exogenous variables are the site or location where the data were collected. And that's something that we need to account for just econometrically. So site would be, in this case, a matrix, and beta would be the number of vector with the same number of rows as there are. The same number of rows, and then if you fix the notation, you'd see that is the way we adjust for which site the person is located at. And then the two random effect parameters that we're interested in is delta theta and delta zeta. So delta theta we model as a random effect. We're going to posit that it's normally distributed we have to, you can see in line 2A that we have to place a scale on the random effect because it's not identified. So we just say it has a unit standard deviation just for identification. And then the systematic component is theta star. Theta star is defined in 2B in order to construct, what we're saying in 2B, which is going to be modeling the group composition effect on the person's latent preferences. The way we construct 2B is we start with 2D, and we create a vector of pretreatment ideal points among the people who are seated at person I's table. So again, if person 1 is seated at a person with persons 2, 3, and 4, then this 2D would extract a vector of the ideal points for persons 2, 3, and 4. And then equation 2C is taking the average of that and creating a variable that's called H. And then H is what feeds into 2B, and you can see that what H is doing is it's modeling the respondents' change in their ideal point as a function of the group composition of ideal points, H. And so alpha 1 is measuring that group level dependence. And then if you read the paper, you'll see that we're interested in our case, in modeling whether that relationship is concave or convex, which is a way of testing whether or not there's polarization within the small groups. And so you have to read the paper to learn more about that. But you can see it's just then that just becomes a quadratic function that lets the shape of the curve differ for liberals and conservatives. And so that's 2B. This is a simplification of the systematic component compared to what we have in the paper, just for the illustration that the simulation is not quite as complicated as the application. So the data generating process shown on this slide we know to be true just because it's based on the simulation. Okay, and then for delta zeta is likewise modeled as a random effect, and it uses the same logic, right? So both 2D and 3C make use of that map variable to keep track of who is with whom. And what 3C is doing is it's taking the zetas for everybody else at your table, and then 3B is taking the average of those zetas of everybody else at your table. And then rho is giving the amount of correlation that remains among this sort of residual form of dependence after we've accounted for ideology. So rho is essentially the correlation of this residual dependence, or it's sort of a measure of the residual dependence among people who are at the same table and seated in the same group. Okay, so that's essentially what we want to do, and now we just need to look at the code to implement that. So with the tutorial, I distribute the code that that implements the model that's tailored to the simulation. And again, it's general it's not limited by any means to our application, but it's something that's flexible and general because you can just read in with the data things like the number of respondents who are in your data set, as well as the number of questions that you're including to construct both the ideal points, which are measured in this part of the likelihood, as well as in the systematic likelihood that's modeling the post-treatment outcomes, which is in this part of the likelihood. But you can see, right, that this just implements this part of the likelihood for the post-test is just implementing that the systematic component that I showed you in equation 1 on the previous slide. This part of the likelihood you can see is extracting the ideal points theta using an IRT logic. And then for priors, they're just listed down here. Here's the prior for theta naught, right? And then and we're setting theta the precision of theta naught down here to 1. And here's the prior for delta theta. It's just implementing that procedure that I just described on the previous slide. And so what it does in order to sort of keep track of the ideal points of everybody else at the table, for each what the code does first is it creates this very long vector called w theta naught, which is the full listing of ideal points for all of the neighbors corresponding to the map variable that we created. So what map is doing is it's extracting the thetas that correspond to the index listed in the map variable that we're going to construct using the pre-processing tools that I'll describe in a minute. And then what w theta is just this ordered list of ideal points that follow the list of people in the map. And then in order to find the average of that, we use this line here to create the h function, which is the average of ideal points. So you can see that now in this case the c variable helps us extract the right indexes the difference in that the c variable is telling us to extract the right indexes from the w theta vector for the ith person, and then the difference in c from the next person minus the c from your person is the number of people in your group. So if there's 4 people in your group, then this difference is going to equal 4. If there's 4 people other than you in your group, then this difference is 4. So anyway, so this line of the code here constructs that h that I showed you on the previous screen, which is in this case is the average of ideal points of everybody else seated at your table. This line is just taking the square of that, right? And then all of that just feeds into the systematic component here, which again is just an exact transcription of the systematic component I showed on the previous screen. And then the same thing works as well for the zetas. So, but of course, because there's a zeta for each question that you ask, right? Because it's specific to each question. What w zeta is, instead of the vector like w theta, it's a matrix where it's the matrix is the length of the number, is the number of rows in this matrix is the number of neighbors in the data set, and the number of columns is the number of questions. So w zeta is just like w theta, except for it has a column for each of the questions that you ask, right? And then otherwise it's exactly the same. We just plug all of that in the same way that we did for theta. So here we're taking the average of zetas for that question for that person, and then rho is the correlation parameter. And then the priors are all pretty much across the board flat priors. The only thing to keep an eye out for is for the IRT part of the model. We need to constrain the parameters for identification to be a given direction. So if we have a set of indicators, we know they're going to be either positively or negatively correlated with each other. So we can put in informative priors that force the factor loadings to all have the correct sign. And if you don't do that, then the model can diverge because it's kind of arbitrary which way the latent variable points. So that's just something to keep an eye out for. But everything else is pretty much just straightforward. In R Studio, you can open up this file called tutorial linear setup.r that was distributed with this tutorial video within R Studio. And you can see the tools that we use to pre-process the data to read out into open bugs. Again, I talked about this. If this is all new to you, then you should watch the tutorial video to make sense of what most of what's going on here. But assuming that you watch the tutorial video or that this is all natural to you, then you can just look at this set of functions. So the first one here is called table ADJ, which is which is just a function that creates a matrix. That's the adjacency matrix that is equal to, for the person I, the column, right? So there's the number of rows equal to the number of people in the data set. The number of columns also equals the number of people in the data set. And so for each person in the ith row, we set 1 in the column of their neighbors. So if person I is seated at a table with 4 other people, there would be 4 1s in the first row, corresponding to the people who are in contact and communication with that person. And so this is just a tool to create the adjacency matrix. And then once you have the adjacency matrix, if you look, this function here, table map, is the function that creates that map vector that I described in the slides. And then this table C function creates that vector C that's keeping track of the indexes in the map that I described as well. And so then just these globally defined map and C variables are the things that we then take and read along with the constants and data. We read those out into making use of this bugs data function that comes from the R2 OpenBugs package. So what we've done is we've created the map and C variable that are just globally defined objects. We set all of the constants here, the number of respondents, number of questions, the number of responses that's set for if we were to do the ordered model, which I'll talk about in just a sec. The number of sites in the simulated data is 3, so that's telling us that there's the number of sites minus 1 is the number of exogenous variables in the model. And then Cn is a constant, which is just a count of how many total neighbors are there. You could think of that as just the length of the map variable. And then the bugs data tools doesn't, it's fine to read out matrices of variables for use in OpenBugs, but in order to do that, you have to convert them to matrices using the as matrix function. You don't want to try to read them out as data frames because the function won't work that way. Anyway, I create some additional variables and the matrix of sites. And then, as I explained in the previous video, the bugs.data function needs these 2 things, which is a list of all of the data and constants that we're going to read out into OpenBugs. And then we're just calling that object data. And then inits is the function that we've defined that generates random values for the starting points for the Gibbs sampler that we'll read into OpenBugs as well. And then obviously set your working directory where you want to put your local files, and then just use these 3 lines to generate the data and to export the data into a file called data.txt, and then it generates and exports the initial files using these 3 lines here. And so we'll have 3 files to initiate the Gibbs sampler in 3 different locations of the parameter space using these initial files, and then the data is in data.txt. And so that's pretty cool. And then now what we can do is just take a quick look at how to open this up in OpenBugs. And in the previous video, I ran a different model, so this will come back and tell me I need to start a new model, so don't be surprised. But what we do is we open up the model. In this case, remember, it's called tutorial linear model. So we open it, and then as I explained in the previous video, the first thing you have to do is just check the syntax, pushing this button, go into the model tab, opening up this menu, and then pressing the check model button. So now it's asking me to replace the one that I had done in the previous video, and so I wanted to do that. And so anyway, so it checked the model for me, and it says the model's syntactically correct. So the next thing we want to do is to load in the data. So we can open up the data. And remember, the data is called data.txt. So we can load the data. And then now remember, we're going to compile 3 models so that we're able to check for, just to verify that the Gibbs sampler, the Markov chain that results from the Gibbs sampling is located inside of a stationary posterior distribution. And so we're going to compile a model that has 3 chains. So it runs 3 instances of the Gibbs sampler. This model is complex, so it takes just a few seconds for it to compile. And now we're going to read in the initial values. So we're going to start with inits1, and then read in the initial values for the next 2 chains. So we have inits2 and inits3. So now we've read the initial values for those 3 chains. Again, because this is relatively simple data, I was able to initialize all of the parameters. That's easy to do. But sometimes for complex models, you end up trying to let OpenBugs generate its initial values for other things that you didn't feel like setting up initial values for. And so usually that works, but if you don't want to try to, as I mentioned in the previous video, you don't want to try to have OpenBugs sample initial values from really diffuse prior distributions, because that can put you into this weird spot of the sample space where just computationally it can't get itself out of. Okay, and so now what we're going to do is tell OpenBugs which of the parameters that we want to monitor. And so before in the tutorial video, there were only 3 parameters or 4 parameters. So I just type those in by hand. But once you use OpenBugs for a while, you want to start using the scripting language. And you can automate all of the steps that I'm showing you. The scripting language lets you kind of automate everything. Mostly I just use it for, I'm usually not in a huge rush. And so I just use it to automate setting which parameters that I want to monitor and save replications from the posterior for. So here, what you do is you open up the script text file that, again, we've distributed with the tutorial, and then you just go to the model menu and press the word script. And you'll see then that we've told it to monitor all of the nodes that we're interested in keeping track of and reporting in our results. And then to run the model, you simply go to model and then to update. You're going to want to run this model for a very long time, particularly if you're going to try to run the application from scratch, because the application, data that's not the data from a simulation is relatively clean. Data from an application is just more complicated, and so it takes a while for it to converge. And you want to monitor the convergence really carefully. But you can update by to have it kind of we'll have to have it start the Gibbs sampler from your starting values by just going to model update, and then the update tool comes out, and then you tell it how many updates you want to do and how often to refresh it. This model is relatively complex, and so the updating takes a while. So it's about, for the simulated data, it's about 1 update per second. So in order to really do this, if we want to run this for 10,000 times, that would be 10,000 seconds, which is like, a little while. But what we can do is maybe just keep track of one of the parameters that we're interested in and see what it looks like as it draws the samples for that parameter. And so you can see that it starts out not stationary. So if it was sampling any faster, you'd see that these chains, the green chain, the blue chain, and the red chain start out sort of in very, sort of wandering around in different locations of the sample space. And so we wouldn't say that at the beginning of this process that the Markov chain was locked into any kind of a stationary posterior distribution. And so what we'd have to do is just let it run for a while until it goes through the burn-in period where we can evaluate and see that the Gibbs sampler, the Markov chain from the Gibbs sampler is indeed locked into a stationary distribution. And you can already see after 78 or so, you can see that the chains are beginning to converge. But I'm going to stop it here just in the interest of time and show the results that once you let it run for a very long time, you get it. I just ran it for a long time and then let it run for a long time in the stationary posterior distribution and saved the results and then graphed them in this document called history. And so you can see that once the model finds that stationary distribution, it gets locked in. And these are all the parameters, and you can scroll through all the parameters and see, actually sort of by the time you would even maybe even think for these lambda coefficients or the factor coefficients for the pretreatment ideal point, and you can see that it still isn't really stationary until you get to about the 5 or 6,000th iteration. So we probably, if I were going to report this in a paper or at a presentation, I would probably discard any observations before the 5,000th iteration, just to be sure that I'm reporting the right posterior distribution approximation. It can happen that the chains just diverge, and that means you either have an identification problem in the model itself, or there's just some kind of empirical identification problem with your data. So, like if you had you're running a dichotomous model and you had one variable that exactly predicts the outcomes, then that was in your model, then the model would diverge. So there's different ways you can run into, either the model itself could not be identified, or you could have empirical identification issues. And if that happens, you have to just kind of simplify the model, maybe drop some variables, try different things. You can drop variables from the systematic components of models. You can add indicators, take out indicators, try a bunch of different things until you find that the model converges. And then once you see it converge, then that might give you some insight into why it wasn't converging to begin with. But then if we having run the model for a long time, we can get the posterior distributions for all the parameters. I probably would have run it for a bit longer if I was presenting this in a paper, because I would want the approximations to be a little bit more exact, that there's still some kind of messiness in the approximations, but it's not too bad. And then you can also use OpenBugs to just get a quick summary of all of the point estimates and standard deviations of the realizations for each of the parameters. So these are just summaries of the marginal posterior distribution for each parameter, right? So this column here are the averages of the vector of realizations from each of the marginal posterior distributions for each of the parameters. And then this column here are the standard deviations. So that's sort of like, well, it's analogous to the point estimates and standard errors you get in a frequentist model. And we discussed this in the appendix to our paper, but we show what the benchmarks are and what these results are, and show that the model does a pretty good job of hitting the benchmarks from the simulated data. And using sort of descriptive alternative approaches don't do such a good job. Okay, and so just another quick thing that the dichotomous model works just like the continuous. But it has you know, a Bernoulli stochastic component and a logit systematic component. So, but otherwise the parameters are exactly the same. And then for the ordered case, it's almost exactly the same, except that we need to use the categorical function in order to model the outcomes. And in the tutorial video, if I spent a little bit of time explaining all the different components of the likelihood for the ordered model, but you can see what we're doing is modeling each of the probability of each of the responses using the P's and Q's, and then the logit linear component is a logit function. So that's the sort of this part is the likelihood for the IRT part of the model, with this being the systematic component. And then this is the likelihood of the modeling the post-treatment outcomes, and the systematic component is here. So these are the ideal points for pre-treatment. Oh, I'm sorry. This whole thing is the likelihood for the. I messed up. So these are the likelihoods for the pre-test outcomes. These are the likelihoods for the post-test outcomes are listed down here. And the reason that I messed up is I forgot that for the first element of the first factor loading, the first factor coefficient has to be set to 1. So that's why I separate out the first item from the other items for the IRT part of the model. And then for this part of the code models the likelihood for the post-test, and here's the systematic component here. And again, if the code for the ordered model seems a little bit puzzling, then maybe take a look at the tutorial video. But everything else is pretty much the same, except again, as I explained in the tutorial video, there has to be a little bit of extra coding and making use of these constraint functions in order to prevent the thresholds. They have to estimate the number of thresholds is equal to the number of response categories minus 1, and then you have to make sure that the thresholds in the computational procedure don't cross over each other, that they stay ordered. And so this constraint function preserves that order. And so that's pretty much it. So once you, it makes sense to start with implementing the plain linear model using the simulated data that we distribute with this tutorial. You'll note that the notation for that simplest case exactly matches the notation in the paper. The notation gets a bit trickier in the other cases as well as in the application, but once you see how the model works and you can use the paper to match up the notation for the kind of simple linear case, and once you once you implement that, then you'll get to see how the model works, and you'll understand both the code and sort of the setup in the code and the way the model works. And once you know that, then the notation won't matter if it doesn't quite match up in the other for the other models or for the application, because you'll understand how to read it at that point. Okay, and so I hope that this was helpful, and I hope that you're able to make use of this model in your own research, and perhaps you'll use it to try to replicate the results that we have in our paper. And thanks so much for watching, and good luck.